A third thin film technology we will discuss is the cadmium telluride. This thin film technology, which has currently demonstrated the lowest cost price per watt peak among all PV technologies. Let's start with the physical properties of cadmium telluride. This semiconductor material consists of the 2-valence electron element cadmium and the 6-valence element tellurium. Its network is a cubic tetrahedral lattice structure where every cadmium atom is bonded to a tellurium atom. A lot of the research activities on cadmium telluride have taken place on industrial level, and First Solar is the leading company in the cadmium telluride technology. The band gap of cadmium telluride is 1.44 electron volts, a value which lies within the optimal range of band gaps for a single junction solar cell. Cadmium telluride has a direct band gap, consequently only a few microns of cadmium telluride is required to absorb all the photons with an energy higher than the band gap. It means that the diffusion length for the charge carriers has to be in the same order to have the light excited charge carriers collected at the contact. N-doping of cadmium telluride can be achieved by replacing the 2-valence atom cadmium with a 3-valence electron like aluminum, gallium and indium. These elements act as shallow donors. N-doping is achieved as well by replacing the 6-valence tellurium atom with a 7-valence electron element like fluorine, chlorine, bromine and iodine atoms. They act as shallow acceptors. A tellurium vacancy acts like a donor as well. P-doping of cadmium telluride can be achieved by replacing the 2-valence atom cadmium with a 1-valence electron atom like copper, silver or gold. These elements act as a shallow acceptor. P-doping is achieved as well by replacing a 6-valence tellurium atom with a 5-valence electron element like nitrogen, phosphorus, arsenic. They act as shallow acceptors. A cadmium vacancy acts like an acceptor as well. In solar cells, P-doped cadmium telluride is used. However, it's difficult to give cadmium telluride a very high doping level. The structure of a typical cadmium telluride solar cell looks like this. On a glass, this transparent front contact is deposited. This can be tin oxide or cadmium stannate, which is cadmium thin oxide alloys. On top of that, the N layer is deposited, which is a cadmium sulfide layer, similar to the N buffer layer in CIGS solar cells. On top of that, a P-type cadmium telluride absorber layer is deposited with typical thicknesses of a few microns. Making a good back contact on cadmium telluride is rather challenging. The material properties of cadmium telluride do not allow a large choice of acceptable metals. Heavily doping the contact area with a semiconductor material improves the contact. However, achieving high doping levels in cadmium telluride is problematic. Copper-containing contacts have been used as back contacts. However, in long timescales they may face instability problems due to the diffusion of copper through the cadmium telluride layer up to the cadmium sulfide buffer layer. Nowadays, a stable antimony telluride layer in combination with molybdenum is used. Here we see the band diagram of a cadmium telluride solar cell. The P-type semiconductor cadmium telluride has a band gap of 1.45 electron volts, whereas the N-type cadmium sulfide has a band gap of 2.4 electron volts. Consequently, the junction is a heterojunction, similar to the CIGS PV device. The light-excited minority electrons in the P layer are separated at the heterojunction and collected at the TCO-based front contact. The holes are collected at the back contact. An important concept I did not discuss for the thin film solar cells is the two types of solar cell configurations: the superstrate and the substrate configuration. A superstrate configuration is a cell concept in which the substrate on which the solar cell is processed acts as the front window at which the light enters the solar cell. A substrate configuration is that either the substrate acts like a back contact or the back contact is deposited on the substrate. Consequently, no light will pass through the substrate. The light enters through a TCO layer deposited on top of the N-type cadmium sulfide layer. Compare this to, for instance, the thin film silicon we discussed earlier. A PIN junction is considered as a superstrate configuration, whereas an NIP junction is a substrate configuration. The cadmium sulfide, cadmium telluride layers are in general processed using the closed space sublimation method. In a closed space sublimation method, the source and the substrate are placed at a short distance from each other, like a few millimeters up to centimeters under vacuum conditions. Both the source and the substrate are heated. The source can be granulates or powders of cadmium telluride. An inert carrier gas like argon or nitrogen can be used. The source is at a higher temperature as the substrate and induces driven force on the precursors, which are deposited on the substrate. The bulk p-type cadmium telluride is formed. First Solar and NTEC are companies producing the cadmium telluride solar modules using the closed space sublimation method. Among new startups moving into the cadmium telluride PV technology are Calixo, Primestar Solar from General Electric, and Abound Solar. However, First Solar is by far the largest cadmium telluride manufacturer in the world nowadays. From 2008, First Solar has an annual production rate of 500 megawatts and more, and was in 2006 and 2007 one of the biggest solar module manufacturers in the world. The record conversion efficiency of lab-scale solar cells is 18.7% as obtained by First Solar in 2013. The open circuit voltage of the record cell is 852 millivolts. The short circuit current density is 28.6 milliamps per square centimeters with a fill factor of 76.7%. General Electric achieved in the same year an efficiency of 18.3%. NREL has confirmed a new record conversion efficiency for a cadmium telluride solar module of First Solar of 16.1%. The current cost price per watt peak of the First Solar products is in the order of $68 to $70 per watt peak and is expected to drop to $40 per watt peak in the future, keeping the cost price per watt peak lower than the solar modules based on crystalline silicon wafers. An important aspect to be addressed is that the cadmium telluride solar cells contain the toxic material cadmium. However, the insoluble cadmium compounds like cadmium telluride and cadmium sulfide are much less toxic. It is important to prevent cadmium entering into the ecosystem. The question is whether the cadmium telluride modules would be a main source of cadmium pollution. A 2 gigawatt per year production capacity as installed by First Solar at the moment would take up around 2% of the total cadmium consumption by the industry and would not yet be a dominant contributor. Nevertheless, recycling schemes have been set up for installed cadmium telluride solar modules. For instance, First Solar has a recycling scheme in which a deposit of $5 per watt peak is included, which covers the cost for the recycling at the end of the module's lifetime. Maybe the biggest challenge for the cadmium telluride will be the supply of the tellurium. Here we see again the illustration that shows the abundance of the various elements in the Earth's crust. As you can see, tellurium is not a very abundant element, so tellurium supply might be the limiting step to upscale the cadmium telluride PV technology to future terawatt scales. On the other hand, tellurium as source material has only had a few users, and therefore a dedicated mining of tellurium has not been explored. In addition, new supplies of tellurium-rich ores have been found in Hsinchu in China. So at this moment it's not clear to which extent the cadmium telluride PV technology might be limited by the tellurium supply. So far we have discussed the inorganic thin film semiconductor materials like amorphous and nanocrystalline silicon, CIGS and cadmium telluride solar cells. In the next block we are going to look at organic and dye-sensitized solar cells. See you in the next block.